Hello everyone, welcome back to Brain Blitz Audios. Today in this episode of NEET preparation, we'll be looking at previous year questions of chemistry in medical entrance examinations in India. Today we're dealing with the chapter General Principles and Processes of Isolation of Elements. This is the 6th chapter in the Grade 12 syllabus for CBSE in chemistry. So this chapter is really a real short one. So let's look at the questions that come from this chapter. So this is the first question. The process among the following which does not involve a catalyst is A. Haber's process, B. contact process, C. Thermite process, D. Ostwald process. So we need to write down their reactions and find out which of these does not involve a catalyst. Again, does not involve a catalyst. So a catalyst is a substance which speeds up the rate of a reaction without participating in it. So when we look at option A, the Haber's process, the reaction is N2 plus 3H2, giving rise to 2NH3. And this takes place in the presence of iron at 400 to 500 degrees Celsius and 150 to 200 atmosphere of pressure. So the iron acts as your catalyst. So iron increases the rate of this reaction. So therefore, option A, Haber's process, is incorrect because it has a catalyst, which is iron. What about option B, contact process? Now, contact process is the process by which we produce sulfuric acid. So this is basically composing of a varied number of steps. So the first step is sulfur plus oxygen gives you sulfur dioxide, and then you have 2 sulfur dioxide plus oxygen in the presence of V2O5 and 1 to 2 atms of pressure, giving you SO3. Now there are processes other than that, so you have to mix SO3 with H2SO4 to give you H2S2O7, and then add water to get 2H2SO4. But we don't need to go all the way because we already know that in this step, we have a catalyst, vanadium pentoxide. So vanadium pentoxide acts as a catalyst in one of the reactions of the contact process. So it involves a catalyst. So option B is also incorrect because it has a catalyst. What about option D, Ostwald's process? Now, Ostwald's process is basically the production of HNO3. So 2NO plus O2 gives rise to 2NO2. And taking the amount of NO2, so that's 3NO2 plus H2O gives you 2HNO3. So the Ostwald's process is known for using the catalyst platinum, and the platinum catalyst is used when NO is converted to NO2. So since the Ostwald process uses the catalyst platinum, it involves a catalyst, so that makes this option incorrect. Therefore, the right answer is option C, Thermite process. The Thermite process is the process in which Fe2O3 in the presence of aluminum is changed to Al2O3 plus 2Fe. So this reaction produces a lot of heat and it's used for welding railway lines. And so therefore, and this does not have a catalyst. So therefore, option C is the right option with regards to the process that does not involve a catalyst. Thermite process is the right answer. Now, let's look at this question. The chief ore of Al, this is short for aluminium, is. So we need to find out which of these acts as the chief ore of aluminium. So what we refer to as chief ore is that the ore contains more amount of aluminium, it also is capable of being extracted profitably. So which of these has more amount of aluminum and which can be extracted profitably? So we have four minerals which contain aluminium. We need to find out which of these is the chief ore. Now option A is cryolite. Now cryolite is Na3Al F6. Now this is an ore of aluminum, but however, this involves more energy, so it's less profitable. Option A is incorrect. Now option B, feldspar, is a collection of aluminium silicates containing sodium, magnesium, etc. So again, this is not profitable. So option C is incorrect. Feldspar is a mineral, but not the chief ore. Now option D, kaolin, is Al2O3.2SiO2.2H2O. So this does not contain a lot of aluminum. It is very less in number. So option D is incorrect. The right answer is option B, bauxite. Bauxite is the most common ore of aluminum, and the formula for bauxite is Al2O3.2H2O. This is the most economical way of producing aluminum. Next question. Froth floatation is a process of A, oxidation, B, reduction, C, refining, D, concentration. So we need to find out which of these set of reactions does froth floatation belong to. So let's look at option A, oxidation. Now, when it comes to turning metal sulfates and carbonates to their respective oxides, we have processes such as calcination and roasting. When it comes to reduction, we have processes such as smelting, electrolytic reduction, etc. When it comes to refining, we have processes such as distillation, liquidation, and then we have further electrolysis, and then we have zone refining, etc. And we have chromatography, vapor phase refining as well. And for concentration of ores, we have hydraulic washing, magnetic separation, and then we have leaching, and also we have froth floatation. So when we have the ore of galena, so what we do is we use froth floatation. We dip it, we put the powdered ore inside water, and then we add a frothing agent, and then when we stir the water very fast, so therefore froth is formed containing the ore, the concentrated ore, so that is then extracted. So froth floatation is a concentration of ore process. So in froth floatation, the ore gets concentrated. The ore that is in it, such as MBBS or ZNS, gets concentrated. So option D is the right option. Next question. Flux is used to remove basic impurities, acidic impurities, all types of impurities, acidic and basic impurities. So flux is a substance which removes impurities and lowers melting point of the ore. by removing impurities. So when we have basic impurities, you usually add an acidic flux. For example, silica. If you have acidic impurities, then you use basic flux such as CaCO3. So therefore, flux can be both acidic and basic. So when you have acidic flux catering for basic impurities, and you have basic flux catering for acidic impurities. So therefore, option D will turn out to be the right option, acidic and basic impurities. The reason why we did not choose option C, all type of impurities, is that some impurities can only be removed by refining the metal. So that happens after converting the carbonates into oxides and then the oxides back into their metals. And then you have some impurities left which are removed by refining. So flux does not remove all kinds of impurities, but it can remove both acidic and basic impurities. So option D is the right option. If you were to write A or B, then basic impurities means that there are only acidic fluxes, which is incorrect. Acidic impurities means there are only basic fluxes, which is also incorrect. So the right answer is both acidic and basic impurities. Let's look at this question. The MacArthur process is used for the extraction of A, gold, B, platinum, C, copper, D, zinc. So what is the MacArthur process? So the MacArthur process is the extraction from sulfide by using KCN. So the example is 4Au plus KCN plus 2H2O plus O2 gives you 4KAuCN2 plus 4KOH, and then 2 of KAuCN2 is reacted with zinc to get zinc cyanide and gold. So in the end, you see that gold is extracted from its sulfide by using cyanide process, by using cyanide such as KCN. So the MacArthur process is also called as the cyanide process. And this process is used for option A, extraction of gold from its sulfides. Option B, platinum. Platinum is already a noble metal, so it's even rarer than gold, and it's mostly found in native state. And copper and zinc both have carbonates and sulfides, and they do not use such strong cyanide processes such as the MacArthur process. They have simpler ways to extract metals such as smelting. So options C and D are also incorrect. The right answer is option A, gold, because gold does form sulfides and gold is a noble metal, so it's kind of hard to use normal methods here. So we use extreme methods such as the MacArthur process. Now, next question. In the extraction of copper from its sulfide ore, the metal is formed by the reduction of Cu2O with. So extraction of copper from its sulfide ore. So copper is getting extracted, number one. And number two, you get copper metal, pure copper, as the product. So the reaction that we're dealing with here is Bessemerization. So in Bessemerization, 2Cu2O reacts with Cu2S to get 6 Cu plus SO2. So when Cu2O is reduced with Cu2S, which is option C, you get pure copper. So using CO would not be practical because here it is roasting and not calcination. FES is present, but it's not found in resomerization. It's found in reverberatory furnace. And option D, SO2, is usually the product that you get after resomerization and the reduction in reverberatory furnace. So it's incorrect. The right answer is option C, Cu2S, because Cu2S reduces Cu2O in the process of mesomerization to get 6Cu plus SO2. The copper here is known as blister copper because of the presence of evolved SO2 inside. So the copper appears in blisters. So let's look at this question. Which of the following is a carbonate ore? Is it A, pyrolusite, B, malachite, C, diaspore, D, cassiterite? So how do we solve this question? We need to write out the chemical formula of all of these ores. So option A, pyrolusite. Pyrolusite is an ore of manganese. It is MnO2. As you can see, it's an oxide ore. So option A is incorrect. What about option D, cassiterite? So cassiterite is an ore of tin. It is SnO3. Again, it's an oxide ore, so option D is incorrect. So what about option C, diaspore? Diaspore, the formula is ALO into OH, so it's a hydroxide ore, so option C is incorrect. The right answer is option B, malachite. Malachite is an ore of copper. It is copper carbonate times copper hydroxide. So this is a carbonate ore. Option B, malachite, is a carbonate ore. So option B is the right option. Next question. Carbon and CO gas, carbon monoxide gas, are used to reduce which of the following pairs of metal oxides for the extraction of metals? So we need to find out which of these are reduced by using carbon or carbon monoxide. So if carbon is used to reduce them, then carbon monoxide can also be used, however, at a higher or lower temperature. So we have FeO, SNO, ZNO, BaO, Na2O2. So Na2O2 is reduced by water. BaO and SNO are reduced by hydrogen gas. So this is a dangerous process, but people use hydrogen gas to reduce SNO and BaO, barium oxide and tin oxide. So FeO has the reaction. FeO plus C gives you Fe plus CO. For zinc, we also have the same reaction. ZnO plus C gives you Zn plus CO. And if it was CO here, then you'll get Fe plus CO2 and Zn plus CO2 respectively. So therefore, iron oxide and zinc oxide are the metal oxides in which carbon and CO gas can be used to reduce them for extraction of metals. So where does iron oxide and zinc oxide come in? Option D. So option D is the right option. In the first option, SNO is given, which is actually reduced by hydrogen gas. In the second option, also SNO is given, which is incorrect. In option C, both the given metal oxides are incorrect. Therefore, option D is the right option. Now, in this question, in the metallurgical process of aluminum, Cryolite is mixed with alumina in its molten state because it decreases the amount of alumina, oxidizes the alumina, increases the melting point of alumina, decreases the melting point of alumina. So let's look at each of our options. Option A decreases the amount of alumina. So cryolite does not do dissociation. So there is no dissociation of alumina when cryolite is added. So therefore, option A is incorrect. It does not decrease the amount of alumina. Option B oxidizes the alumina. Alumina is Al2O3, which is already inert. Al2O3 is used to coat aluminum vessels so that they become non-reactive. Once they are settled, they do not react again in most situations. So oxidizing alumina is kind of very highly unlikely. So option B is incorrect. What about option C? Increases the melting point of alumina. The melting point of alumina is 2000 degrees Celsius. And at this temperature, which is pure alumina, electrolysis does not take place. So therefore, no refining. So if alumina in the pure state does not undergo refining, then if you start increasing the melting point, then no refining takes place. So option C is also incorrect. And by describing the fault with option C, we also get our answer, which is option D, decreasing the melting point of alumina. So alumina is 2000 degrees, while aluminium itself has only 1800 degrees Celsius. And since alumina is and since in the metallurgical process we need to ensure that alumina is conductive, what we did is that we added cryolite and CaF2 to the mix so that the melting point of alumina decreases, which makes it electrolytically active. So option D, decreases the melting point of alumina, is the right option. Next question. Match list 1 with list 2 and select the correct answer using the codes given below the lists. So list 1, cyanide process, floatation process, electrolytic reduction, zone refining. List 2 contains ultra pure germanium, pine oil, extraction of aluminum, extraction of gold. And here are the codes: 1C, 2A, 3D, 4B, 1D, 2B, 3C, 4A, 1C, 2B, 3D, 4A, 1D, 2A, 3C, 4B. So let's find out which of these are the easiest. Now, remember that in an earlier question, we have defined cyanide process as the MacArthur process, because the MacArthur process uses potassium cyanide in order to reduce the sulfides of gold. So the cyanide process is used for the extraction of gold. So 1 matches up with D. So when 1 matches up with D, that makes options A and C incorrect because they contain 1 as C, while the correct answer is 1 is matched with D. Now let's find out the next easiest way of doing things. You notice that pine oil was described as a frothing agent. And where do you find frothing agents? In froth floatation process. So that means 2 is matched up with B. So 1 matched up with D and 2 matched up with B gives you the right option as option B. instead of option D. In option D, it says that 2 is matched up with A, which is incorrect. So according to this, we have 3C and 4A. So electrolytic reduction is again used in the extraction of aluminum. We're studying electrolytic processes of metallurgy before learning the extraction of aluminum, so 3C is correct. And zone refining is used in semiconductors such as silicon and germanium. So therefore, we get ultra pure products in zone refining. So zone refining gives you ultra pure germanium. So 4 matches up with A. So that's why just by analyzing 2 of our options, we got option B as the right option. Let's move on to this question. Sulfide ores are common for the metals AgCuPb, AgCuSn, AgMgPb, AlCu, and Pb. So over here, we're looking for the common ore. And that ore has to be a sulfide ore. So let's look at each of our options. So we have these metals such as tin, and then we have magnesium, then we have aluminum, and then copper, and then we have lead and silver. So for tin, the most common ore is tinstone, which is SnO2. And for magnesium, the most common ore is MgCO3, magnesium carbonate, which is magnesite. So far, both of these are not sulfide ores. So that means options B and C are incorrect. What about aluminum? Aluminum has bauxite as its ore. And you know the formula for bauxite, right? It's most commonly found as Al2O3 times 2H2O. So therefore, option D is also incorrect. The right answer is silver, copper, and lead. For copper, it is CuFeS2, that is called copper pyrite. For lead, it's PBS, which is galena. For silver, it is Ag2S, which is known as argentite or silver glance. So these are sulfide ores, the common sulfide ores. So that's why option A becomes the right option. So this question is also a match type question. So what we have to do is we have to match list 1 with list 2 and select the correct answer. So list 1 contains titanium, silicon, and then aluminum and lead. List 2 contains bauxite, cerussite, Van Arkel method, zone refining. So let's look at which of these could be correct. So let's find out the easy ones. We already know that zone refining is found for semiconductors. So therefore, 2 matches up with D. And for aluminum, the term bauxite is very common because aluminum has bauxite as its common ore. So 3 matches up with A. So let's look at our options. We have 1B, 2A, 3C, 4D, 1B, 2C, 3A, 4B, 1C, 2A, 3B, 4D, and 1C, 2D, 3A, 4B. So we found out that 2 is equal to D. and 3 is equal to A. So therefore, when you find 2 matches up with D, you instantly get your right answer as option D. In all of the others, 2 is given as either A or C, which is incorrect. Now, in order to complete the matchup, let's look at the other ones. 1 is C and 4 is B. So titanium, Van Arkel process, yes, it is correct because Van Arkel method is usually found for titanium and zirconium. So you get ultra pure titanium and zirconium by using iodine. And for PB, it is cerussite. Cerussite is an ore of lead. It has the formula PbCO3. So this may not be the common ore of lead, which is galena. However, this is also an ore of lead, cerussite, which is PbCO3. So therefore, option D becomes our right option. Let's look at this question. The main reactions occurring in the blast furnace during extraction of iron from hematite are, and we are given 4 sets of reactions. We need to find which of these happen in the extraction of iron, and using that, let's find out which is the correct option. So extraction of iron is from hematite, and hematite is Fe2O3. And it has the impurity SiO2. Now this impurity is basic. This impurity is acidic. So therefore, we must have a basic flux added to it, which is CaO. So therefore, one of the reactions that happen in the blast furnace have to do with forming the slag of the flux, CaO, and the impurity, SiO2. So that is the 4th reaction, which is CaO plus SiO2 gives CaSiO3. Now, in the blast furnace, the temperature is greater than 1273 degrees Kelvin. So at these temperatures, 2 carbon plus oxygen gives 2 carbon monoxides. And this reaction has a lower value of delta G, that is the Gibbs free energy, than the reaction 2Fe plus O2 gives you 2FeO. So because of this condition, Fe2O3 reacts with carbon monoxide. So this reaction is found in statement number 1. Reaction number 1 is Fe2O3 plus 3CO gives you 2Fe plus 3CO2. So these are the 2 reactions that occur, reaction 1 and reaction 4. Note that the other reactions can occur. However, for our specific condition for hematite that happens greater than 1273 degrees Kelvin, we only get reactions 1 and 4. So option C, reactions 1 and 4, gives you the right answer. Option A is incorrect because it states reaction 3 comes in, and option B says reaction 2 comes in instead of 1, and option D says 1, 2, and 3 are involved, where 2 and 3 are actually not. So option D is also incorrect. The right answer is option C, 1 and 4. Now, note that in blast furnace, there are three types of reactions in which iron ore is reduced to iron. So these depend on the temperature and the Ellingham diagrams. So for more of that, you can watch our mind map on this chapter, where we'll be explaining the Ellingham diagram and the various ways in which iron ore reacts. So for this condition, it's hematite and it's greater than 1273 degrees Kelvin. So option C is the right option. This is our final question. 2CuFeS2 plus O2 gives you Cu2S plus 2FeS plus SO2. We need to find out which process of metallurgy of copper is represented by this equation. Now, this actually is pretty easy. When you look at the reactant side, you see that you have CuFeS2. Now, this is known as copper pyrite, and the presence of sulfur indicates that this is a sulfide ore. And what do you do to reduce sulfide ores to their respective oxides? The process is called roasting. And you see you have O2, the presence of oxygen. So therefore, this reaction represents the process of roasting. So copper pyrite is getting roasted. So that's why option B is the right option. In terms of concentration, the process that is used is froth floatation. In terms of reduction, what happens is Cu2S reacts with 2Cu2O to give 6 copper plus SO2. Again, this is a process called mesmerization. And for the purification of copper, we use processes such as poling and electro refining. Poling is the refining of copper using hydrocarbons such as methane. So therefore, the right answer with respect to the above reaction is roasting. Now here how we did it by looking out the reactants. So one of the reactants we know is copper pyrite. Copper pyrite is the sulfide ore of copper. And when you have sulfide ores, you usually do roasting in a reverberatory furnace. So option B, roasting, is the right option. That concludes this episode of NEET preparation. The chapter has a lot of information, and so therefore we recommend watching our mind map on the same chapter. So we also have a lot of useful and interesting information about NEET in our playlists: NEET Physics, NEET Chemistry, NEET Biology. I'll be providing their links in the description down below. So you can click on that and then you can enjoy more information and more quality classes. So if you want to maintain connection with finding out more useful and interesting content, then don't forget to subscribe to our channel, Brain Blitz Audios. You can also hit the notifications button for receiving the latest of our useful and interesting content, such as learner words, mind maps, memory hacks, English lessons, etc. So until the next webisode, take care, stay safe, bye-bye for now.